In our instructional video in Chapter 19, we're going to be talking about our third topic, waxes, in the chapter on lipids. We begin with our definition of a wax in terms of its chemical composition. Waxes are esters that form from a fatty acid and a high molecular weight of an alcohol. So that fatty acid, that long carbon chain that ends up in that COOH, the COO functional group, and an alcohol, we know with a very high molecular weight, has a long carbon chain and the functional group of a hydroxyl, OH. We're going to write down its general structural formula. And when we do so, we just let the letter R represent the long carbon chain that leads into the carboxylic acid functional group, COO, where the H from the carboxylic acid has been replaced by another long carbon chain, creating what we referred to as the ester family from our previous chapters. RCOOR is an ester. What we're emphasizing is these R's are an extremely long carbon chain. When we form a wax, it really is just a combination reaction where we take that long fatty acid, and remember this term acid is very specific in organic chemistry to that COO, the carboxylic acid functional group, and that this is the acid proton on the oxygen. That R chain is a very long carbon chain. We react that with an alcohol, and the alcohol we said is the functional group of a hydroxyl group, but we're emphasizing this particular bond between the hydrogen and oxygen as the site of attachment when we combine the acid to the alcohol. So the reason we're extending this bond is to let us see where the new attachment will form in the wax. And a nice color coding job here. Notice the wax is an ester. We need to remember that a wax is a class of an ester. The original fatty acid, which is the COOH, is retained in the final wax structure. And then the OR functional group from the original alcohol is attached onto that carbonyl carbon. We have a new CO bond that forms. And of course, we can also see how water molecule, an H and an OH, have split out in the process of dehydration. To remove water is a process known as dehydration. So to kind of go through this general mechanism again, to build a wax, we begin with a carboxylic acid, a fatty acid from our previous section with the long carbon chain. It reacts with an alcohol, the H from the alcohol portions of the hydroxyl group, along with the OH part of the COOH, combine to make a water, and the new site of attachment is the oxygen from the original alcohol bonding to the carbonyl. Let's look at a very specific example and kind of emphasize the mechanism again. Below we see a formation of spermaceti wax, isolated from the heads of sperm whales. We may know that harvesting whales has now been outlawed, but the blubber from whales is very desirable in some markets, especially in China and other Asian countries. We begin with a carboxylic acid, and I want to emphasize, we know that it's a carboxylic acid because I see the COO functional group, COOH, COO. This particular acid, palmitic acid, is a total of 1 plus 14 and 1 more gives me a 16 carbon carboxylic acid. We're reacting that with an alcohol, and I see that this is the alcohol functional group. I see the OH. We're emphasizing where the new site of attachment will be by lengthening the bond between the hydrogen and oxygen of the hydroxyl group in the alcohol. This particular alcohol is 1 plus 15 more. This is a 16 carbon alcohol unit. So we have the functional group of an alcohol and a functional group of a carboxylic acid combining to make a wax, which we know is the chemical functional group family of an ester. So when I think about what happens, the C double bond O, that's the carbonyl carbon, is now going to be attaching to the oxygen from the alcohol, and we split out the H from the alcohol and the OH from the acid, and we make a water, HOH. And the new site of attachment is now this ester linkage between the original carbon of the carboxylic acid and the oxygen from the alcohol. And notice on the left side of the carbonyl, we have 16 carbons. And again, on the right side, we still retain 16 carbons. By producing a wax, we combined a carboxylic acid and a primary alcohol. In a dehydration process, we remove a water and create a new linkage of C single bond O. Because of their very long nonpolar carbon chains, waxes are very hydrophobic. And we know that hydrophobic means water hating. Literally, that's the interpretation of hydrophobic, water hating. So they're very good at forming protective coatings, for instance, in birds' feathers or sheep's wool, or they are the primary ingredient in beeswax. Beeswax, we're kind of showing you the chemical formula here. We have a very long hydrophobic region. This is a 15 carbon chain plus one more here. So this is a 16 original unit there of the carboxylic acid. So let me just emphasize that a little better with highlighting. The original carboxylic acid would have contained 16 carbons. And then down here, notice on the alcohol portion has a total of 30 carbons by the time we're done adding those together. And the only region really that is polar in this entire molecule, the polar region being where the C double bond O and then so right there, the hydrophobic region is a long carbon chain on both ends, long carbons. And then the hydrophilic is that tiny little spot in the middle where we see the C double bond O. But by far, the long carbon chains make this structure very hydrophobic. So our general structure of beeswax, all you had to do was draw its general structure, where we see a 16 carbon original carboxylic acid attached to a 30 carbon original alcohol to create a long carbon chain known as beeswax. Well, let's take a look at a very specific example here. It asks us to draw a structure of cetyl myristate, a minor component of spermaceti wax. It's formed by a 14 carbon fatty acid chain and a 16 carbon straight chain alcohol. And when you hear straight chain, you can just think of that as being a primary alcohol. So as we begin, I like to write my carboxylic acid on the left, and that serves as the attachment with the alcohol that will form the ester linkage in the right. So we start with a 14 carbon fatty acid chain. When I hear fatty acid, that's the Q. We have 14 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 by the time I'm done counting. Let me be sure. There are indeed 14 carbons. Now on that 14th carbon is the carbonyl C double bond O. It goes down to form the ester linkage. And now we have to attach 16 carbonates that came from the alcohol. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's count to be sure. Looks like I have it correct. So we had a carboxylic acid, the original acid of 14 carbons. On the right side, the original alcohol contained 16 carbons. We can see the ester linkage. The ester linkage where the original alcohol is now attached to the original carboxylic acid, creating a wax. Spermaceti wax has this a minor component that we just drew. And we tear that down, we're looking at the structure of the original acid we just drew having 14 carbons. The original acid, 14 carbons, and notice I say acid, that's the COOH, the COO formation. And when it combined with the alcohol that had 16 carbons in it, we formed a general wax formation, and we understand that waxes are a type of ester. So just kind of an opportunity to recheck what we drew on the first page there. So drawing the structure of cetyl myristate, a minor component of spermaceti wax, formed from a 14-carbon fatty acid and a 16-carbon straight chain. We were able to complete the wax structure. And remember, we called this a dehydration formula. Splitting out a water dehydrates the molecule. Think about this with me. Here's that structure of beeswax again, and it's said to be insoluble in water. As we know, all fats are insoluble in water. Wax is a category under the family of fats, lipids. Slightly soluble in ethanol and very soluble in chloroform. Let's explain why. Well, first of all, let's remember that our general rule of solubility is likes dissolve likes. So we understand that beeswax is a very non-polar molecule by far, with these incredibly long carbon chains. Those long carbon chains are hydrophobic, and literally that translates to water-hating. A water-hating molecule. So insoluble in water, we'll decide that makes sense because water is a very polar molecule. And so therefore, that would not follow the general trend of likes dissolve likes. We understand that the beeswax is non-polar, very hydrophobic, so it is insoluble in water just because they're opposites. Non-polar will not dissolve in polar. The next one it gives us is ethanol. Ethanol, I would say, is slightly polar. And it is so because it does have a little carbon chain. The carbon chain is the non-polar region of the molecule, and the OH group would be polar. So since it has a little more quality of non-polar than the water molecule, it is indeed slightly soluble. And by the time we get to chloroform, that's the third choice up there, CHCl3 is chloroform. This is a very non-polar molecule. It's symmetrical in most regions, and it's kind of an even distribution of electron density. And so likes dissolve likes. Yes, this would be soluble simply because likes dissolve likes. So we've decided beeswax is hydrophobic, only soluble in other non-polar solvents like chloroform. We said it was insoluble in any polar solvent like water, and it would be slightly soluble in ethanol that had a carbon chain qualities of a non-polar with its polar solvent. And let's drive that home with another practice about solubility and thinking through about formations. We're asked in this practice question to draw the structure of a wax formed from stearic acid. So here's our stearic acid, carboxylic acid functional group there, COOH, and each of these alcohols. So the difference in the structure is only going to lie on the right side of the wax that we form. So let's model letter A. We begin by writing out the acid, and it started with a methyl group, CH3. In parentheses, we have CH2 taken 16 times, and then finally the COOH, COO. And remember what we're doing when we form these, we take the OH from the acid and the H from the alcohol, and we split out to make a water. So this is a dehydration process. And what attaches then is an ester linkage that originates from the alcohol, the O on the alcohol right here. It's attached to CH2 taken 9 times and ends with the methyl group. This is the wax that would form from stearic acid and a 10 carbon chained alcohol. Letter B. We start with the same carboxylic acid, so the left side of our wax has the exact same structure throughout all of this problem. What is only going to be different is the original primary alcohol. This time the alcohol has 11 groups of CH2 units, ending with the CH3. And finally in the letter C, we're seeing the pattern. CH2 taken 16 times, the carbonyl carbon, now bonding to the oxygen from the alcohol. And this one has 30 carbons altogether. So in a row, we'd have CH2 taken 29 times and ending the tail with CH3. Pretty comfortable with those practices. Let's look at a little bit of the chemistry now for waxes and how they can undergo hydrolysis. So friends, what we were just practicing, dehydration, is now going to be reversed through hydrolysis, adding water across the bond. And so it's just a forward and reverse reaction. Here we have a wax and we're adding water, and out comes the parent carboxylic acid in the fatty acid group because it's such a long carbon chain, and the parent, primary alcohol. And so it's really just a game of detective. What must have been the original carboxylic acid and alcohol to give us the wax structure that we're looking at? We know that we simply cleave the bond of the carbonyl group. The carbonyl group is the wax component coming from the acid, and the primary alcohol group is on the right side of your structure. So these will be quite easy. Here is a wax, just kind of looking this through, and my eyes go to this C double bond O ester linkage right here. So I understand that on the left side, the side that contains the carbonyl carbon originally came from the carboxylic acid. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons originally from the carboxylic acid. So we could write CH3, parentheses, CH2 taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. And finally, we have the COOH, the carboxylic acid that is 12 carbons long. How about the alcohol side? On the alcohol side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. So to write the alcohol, we begin with that last CH3 group. Well, we can write it in this direction. We can write the alcohol, and then bonded to it were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 CH2 groups terminating at the CH3 at the end of the chain. And that gives me 16 carbons altogether. So the original fatty acid is a carboxylic acid, and the original alcohol have been formed. The process is hydrolysis, so you would see an acid sitting on the arrow. Add water is another way that you'll see hydrolysis, and you're just breaking the ester linkage, giving back to the original carboxylic acid and the alcohol. When ready, come back and start your lesson in section 19.4.